and as it relates to algae, is a legend in his field. Stephen is the founder and CEO of a company called Algenesis Materials. It's a company on a mission to reduce plastic pollution on the planet. He'll tell us more about that shortly. He previously was a distinguished professor of biology and the director of the California Center for Algae Biotechnology at the University of California in San Diego. His research career focuses on the molecular genetics of green algae and the production of bioproducts, especially bio-based and biodegradable polymers. Steve received his bachelor's degree in biochemistry and plant biology from the California Polytechnic State University in San Luis Obispo, and a PhD in molecular genetics from UC Berkeley. Following a postdoctoral fellowship at the University of Geneva in Switzerland, he returned to California as an assistant professor at the Scripps Research Institute, where he remained for 22 years, becoming the Dean of Biology before joining UC San Diego in 2009. In addition to running his research group and University Research Center, Steve also founded Rincon Pharmaceutical in 2005, Sapphire Energy in 2007, Trident Health and Nutrition in 2013, and Algenesis Material in 2016. Stephen, you represent what here at the Institute we call academic entrepreneurs, and we really look forward to your talk. So without delay, the floor is yours.
Perfect. Thanks, Maurizio. And thanks, everybody, for tuning in. Let me make sure that you guys can see these okay. Are we good with that? Can we see them?
Yes, you can.
Okay, good. All right, I'll jump into this quick. As Maurizio said, I'm Steve Mayfield, still emeritus distinguished professor of molecular biology. Somehow I still have two students at UC San Diego. I retired, they haven't yet. But what I'm going to tell you about today is sort of what I've been working on for, I don't know, many years, but certainly the last decade. Because although I started out as very much an academic guy, sort of about 20 years ago, I sort of recognized that we had lots of problems in the world and that publications, although they're super important and discoveries are super important, it's actually products that change the world. And so I pivoted and sort of went more down the application route. And we'll talk a little bit about that today. But first, let me I want to spend a little time and tell you, where I think we are today, how we got there, give you at least one of the potential solutions to some of our problems, and then maybe a little philosophy on what we can all do to sort of get us out of this mess. So question number one is, how did we end up here, right? And is it even possible for us to reverse this now? And this being what we humans have done to this planet and continue to do and are accelerating, right? But let me just give you a little my short world history, okay? So number one, this is brought about, everything that we see, everything that we do, everything that we are today is brought about by our exploitation of fossil energy. And this is, let me see if I can get, where's my little, can I get a pointer here? Oh, that's okay. I think you can probably see this. Anyway, this is fossil energy use for the last 200 years. I mean, most fossil fuels, if you're talking about coal, they're at least 500 million years old. If you talk about oil, petroleum, and natural gas, some of those things are 800 million, a billion years old. And we've really only exploited them, amazingly enough, in 1850, right before the Civil War. These things were unused. We had traditional biomass. People were burning wood, but we didn't really use them. And it was really when the Industrial Revolution kicked in that these things really took off. And then you can see by this graph, the real inflection point came right after World War II, where we industrialized the entire world and put everything on hyperdrive with energy from fossil sources, right? So this is a picture of worldwide GDP, gross domestic product, per capita over the last 1,000 years, right? How long have humans been on the planet? I don't know, 1 million years, some people think. Others only a few 100,000, but certainly we've been here longer than 2000. And if you look at this, for most of our history as human beings, we all lived in poverty, right? It was really hand to mouth. And it was correlating quite strongly with the Industrial Revolution and the use of fossil energy that economies, the way we know them today, economies really took off, right? And here you can see the United States is sort of leading it. Here's one that's really interesting. So this is China, and not shown on this graph is India, but it would be right behind it. And if you notice, they didn't really take off until 2000. It's only been 25 years since the Chinese economy really kicked into gear. Biggest economy in the world now, past the United States several years ago. Um, that was brought about and correlates quite closely with the use of fossil energy. The corollary of that, sort of the other side of that is that worldwide poverty has declined significantly. And these are the ones that I always find amazing, right? So here's 1820. In 1820, 200 years ago, 94% of the people on this planet were living in poverty, right? $2 a day. That meant they had enough money to feed themselves, but not much beyond that. 84% of people lived in extreme poverty. Extreme poverty means you have food insecurity. You do not know where your next meal has come from. You are literally living, whatever you can gather or collect that day is kind of what you eat. 84% of people. And over the last 200 years, because of fossil energy, because of the growth of the economies, because of growth of wealth on this planet, that number is now down to single digits. Certainly extreme poverty is down to single digits. Poverty is, maybe 7, 8% of the population. And most of that, by the way, brought about because of wars or because of other circumstances, not so much just whether they can work or not. So fantastic, right? Believe me, I've never lived in poverty. I never want to, but that is one fantastic thing. But here's sort of a little alarming graph, which is if you put the two of these things together. So now you put together fossil use, that's shown here in blue, and then shown in red is world population, which is about 8 billion people, a little over 8 billion people, 8.02 billion people, right? Kind of a shocking thing for me is that when I was born, I'm 69, so in 1955, when I was born, there were only about 2.5 billion people on the planet. So in just my lifetime, we have added 2 more planets worth of people. And as I showed, economies are booming. We have 8 billion people, and they're relatively, by historical scale, they're rich. They're rich beyond belief, right? So what does that really mean? Well, number one, rich people love to drive cars. We all have them in California. We have 1 car per person. A lot of people under 16 don't even have driver's license. Somehow we have a car ready for them in California, right? This happens to be a picture of the freeway up in Los Angeles, actually pretty close to UCLA. But this could also be San Diego looks the same now. Houston looks the same. San Francisco looks the same. The world looks the same. Shanghai looks worse, right? We just have a lot of people driving cars. And we have a lot of people flying around the world on airplanes, right? Because we like to travel and we like to be mobile. Here's another little kind of interesting tidbit for you, which is as people gain wealth, as you become more wealthy, you tend to eat more of your protein as animal protein. So what this is a plot of gross domestic product going this way, percent of animal protein of your total protein consumed. Here we are, United States, very rich, bunch of other rich countries you see up here, Japan, Sweden, Switzerland, etc. We all have a very high content of animal protein. That's not to say that people need protein. So what happens if you're down here? What happens if you're Indonesia, Nigeria, Bangladesh, right? You still eat protein, right? It's just that comes from plant sources because plants are much cheaper than animals, primarily because the efficiency, right? In order to make an animal protein, first you have to make a plant protein, then you have to feed it to an animal. There's some conversion efficiency. It's usually pretty small. Beef is the worst. Some people think it's 10 to 1. About the best I've ever heard is 4 to 1, means 4 pounds of plant protein of soybeans or corn to get you 1 pound of beef. So the richer we get, the more of that we eat. Okay. And here's one that is just my personal peeve, and I will tell you a little bit about how I'm directly trying to address this. And that's because we're all rich, because we all live like kings, let's make life really easy and never wash a dish again. Let's make everything single-use disposable containers. That bottom picture of coffee cups, Starbucks alone produces 8 billion, with a B, 8 billion coffee cups per year that are neither recyclable or compostable. They simply go into landfills. The one that I find mind-boggling is the one on the left, which is we have these things, fruits and vegetables, that come prepackaged, okay? They have to survive in nature. They have to be out on a tree or on a vine or whatever. So what do? We cut that packaging off them and repackage them in plastic, which we then use one time and throw away. And I'm actually going to talk a little bit about plastics, right? Like I said, it's one of the things that I think we can easily change, and I'll show you how we have an opportunity to do it. But look, given all of that, given that we're rich, given that we're consuming a lot of animal protein, right? What could possibly go wrong, right? Well, for one thing, we could have a change in climate, and we do, in spite of some political statements that you've heard lately. I doubt if anybody really believes that the climate isn't changing. All right. It's expedient to say that it's made up, but 2023, as you guys know, was the hottest year ever recorded. July of 2024 was the hottest month ever recorded. That supplanted July of 2023, which was the previous record, and on and on and on it goes, right? The climate is changing. When I was born, you could grow corn in Texas, about halfway up Texas. The Corn Belt started and it ran to about 80 miles south of Canada. In the ensuing 70 years, you can no longer profitably grow corn in Texas. The Corn Belt has moved north more than 80 miles, and you can now grow corn in Canada, right? So this is clearly real, significant consequences. I won't belabor those, right? Sadly, because we consume so much animal protein now, the way we get that is by growing primarily corn and soybeans and feeding that to cows and chickens and pigs. And so we've surpassed our ability to produce enough of those using our traditional agricultural land. So we've started to expand that. And how do we expand that? We do it by deforestation, cutting down the grasslands, cutting down the trees and planting soybeans and corn. I'll say this. If you just Google Cargill soybeans and rainforest, you'll find a couple of articles written by the New York Times from a half a dozen years ago that explains exactly how bad this is and how rapidly it's going. Okay. And then, as I said, we're going to talk a little bit about this one because this is my personal peeve, right? I spent a life at the beach. I grew up on the beach in Hermosa Beach, not far from you guys at UCLA, surfed all around the world, and every place I go and every place I've ever been over the last 10 to 20 years covered in plastic trash, right? The entire planet. And we know why. It's convenient, it's cheap, never biodegrades. 17 trillion pounds of plastic on this planet right now. That's about 2,600 pounds for every man, woman, child alive today. About 18 billion pounds of plastic flow into the ocean every year. And like I said, this is just for convenience. When I was a kid, we didn't have plastics. We weren't suffering. We had shoes, we had cars, we had containers. They just were not made out of polyethylene or polypropylene. There's a couple of different pictures here. The one in the middle is one I took on the Maldives Islands. That's a set of islands out in the middle of the Indian Ocean, about halfway between India and Africa. And I was down there right before the pandemic. I was down there in 2018 and surfing, taking a boat around. And last day, asked the captain if he could take us by an island that people had never walked on. And he said, well, I don't know about never walked on, but they probably haven't been there in 20 years. So we stopped by this beautiful little island right down by the equator. And on the windward side of it, it was covered with dead flip-flops and toothbrushes and plastic bottles, right? And these did not come from the locals. These were washing in from from India, from some river in Indonesia, who knows where. There was also a group down in Australia that did the same thing. That's this picture in the upper left-hand corner here. They went to an island about 1,800 kilometers off the coast of Western Australia, an island that they knew people hadn't gone to. It was covered in about 18 inches of plastic trash. Again, plastic bottles, fishing nets, flip-flops, you name it. The oceans are now filled with these things. Okay. And then here's one that I think we've only really started to recognize just how significant this is going to be. It's all of those plastics that are out there are being abraded, right? If you're in the ocean, if you're on the land, it doesn't matter. UV is breaking them down, abrasion, cracking, wind, movement. And now there are microplastics in every part of the world. They're in our drinking water, they're in the ocean, they're on the top of Mount Everest, they're in the bottom of the Marianas Trenches. They are everywhere. Everywhere we measure, we get a huge number of microplastics. We've now started to find them inside of our own bodies. They are in the plaques on our arteries. And a really alarming one showed up earlier this summer where a group out of New Mexico looked at the brains of people who had recently died and found that on average 0.5%, a half a percent of our brain is now made up of microplastics. And these things are having significant health consequences. Okay. Okay, so kind of depressing, but where did we get, right? Why are we here, right? We're here because what I would call total world consumption has just simply blown past any kind of our ability to sustain that or to contain it, right? And that is the number of people times the amount each person consumes times the efficiency of production or the method of production, right? And there are solutions, right? I'm going to tell you about one example of a couple of things I look on with algae for a couple of solutions. There are others. We just don't like any of them. All of them require us to do something different. It's not even so much sacrifice, right? There's a bunch of stuff that we just have to do different. And as humans are funny, we want to do today what we did yesterday, even if what we did yesterday was unhealthy, was bad for the planet, and didn't make any economic sense. Damn it, we don't care. We want to do the same thing. But this is just a quote from Will Rogers. Hope you guys know who he is. He says, if you find yourself in a hole, the first thing to do is stop digging. And we seem to have an inability to do that. But I'll also give you another one of my favorite quotes. This actually came from the vice president of Exxon. And we were talking 10 years ago about biofuels, and Exxon at the time was supporting algae biofuels. And I was asking him, what do you worry about? Running out of fuel, climate change, et cetera. He said, I worry about all those things. But the number one thing I worry about is people only operate in two modes. They do nothing and then they overreact, right? And he said, for the longest time, humans just hope somebody else solves the problem, right? They'll ignore it. They'll think that's not my job to solve it. He goes, but at some point, the problem becomes so oppressive and so damaging that then they do stuff. And generally by that time, they have to over-respond. Then he paused for a minute and he said, and every time they over-respond, they take it out on me, which I would argue probably deserve it. But at any rate, so my hope is that we start to recognize just how significant the problems are. And we do overreact to these a bit and start to adopt some of the solutions, start to take up some of them. And now I'm going to tell you about what some of the solutions I think that we can achieve pretty easily. We can integrate into our economy pretty easy. So let me start just by saying this. I've worked on algae for 30 years, continue to. I'll tell you a little bit about a shoe company we've started, or a polymer company, and one of our products is shoes. We use algae oil for that, but we also use plant oil. So where I say algae, this could be any plant, right? So what we're talking about is photosynthetic biomanufacturing, right? What does that mean? That means we take sunlight and CO2 from the atmosphere, and we use the process called photosynthesis to convert these water, nutrients, and CO2 into all kinds of things. I mean, obviously, we recognize these as food, whether that's a corn or a tomato or you name it. But we can also engineer plants and algae to make anything we want. We can engineer them to make pharmaceuticals. We can engineer them to make plastics, to make fuels, you name it. Technically, we have many of the solutions available now. We just don't use them, Okay. Okay, so why algae and why do I think that this is something that's worth investigating? A couple of different reasons. Number one, most of our plants are right now just barely keeping up with the food production that the world needs. So if we're going to start to make interesting new things, whether that's biofuels or plastics or any of the other things we might make with photosynthetic biomanufacturing, we probably shouldn't compete with food. Algae are a new platform. They do not compete with food. They're very productive. All right, I'll show you a little bit of what that means. They're scalable, means obviously you guys know algae grows every place on the planet, grows in the oceans, grows in freshwater, grows on rocks, grows. It's the original savior of this planet, right? All petroleum comes from algae. It was one of the first organisms to ever show up. It's the reason you and I can breathe. It's the original good neighbor. Okay. Sustainable means that doesn't do us any good if we're going to grow a bunch of algae if we're going to have to use up some other limiting resource like fresh water. Algae grow in brackish or even full on saltwater. They'll grow in the ocean. So they can be extremely sustainable. Programmable means that all of us, collectively have arrived at the point where if we find a new organism or we want to engineer a new trait into an existing organism, we can do it, right? And we can do it very quickly. Another kind of cool thing about algae is they're already edible. There's a bunch of products we're going to make that aren't necessarily food, but I'll show you food is one of the really important ones we can make, whether we eat it directly as humans or whether we use it to feed cows and chickens and pigs, either one of those, it's edible and that's important. Okay. Okay, so when I say they're productive, what do we really mean by that? Here's just a couple of really quick examples. One, obviously, we started this working on biofuels, and that was oil content. The sort of standard out there right now was either soybean or palm oil. Those are kind of the two big ones. Don't get anything between 40, 50% oil content. What does that convert in? That means palm, which is the most productive oil crop on the planet, 600 gallons per acre per year. Algae, no problem at all. We're well above 2,000 gallons per acre per year now. We could go to 5,000. Here's the standard for protein, though, and I think this one is equally interesting. Soybeans are the gold standard for protein. It's where most protein on the planet comes from. We use it to feed to animals. We use it to put in, protein bars, you name it, 350 pounds per acre per year. Algae, we have plenty right now that'll hit 10,000 pounds per acre per year. So just in a pure productivity, nothing else touched these things, right? Why don't we use them for everywhere now? Because because they were not a terrestrial plant, they weren't immediately available to humans. They were everywhere. They were ubiquitous and they were everywhere, but we really didn't domesticate them. We didn't turn them in to an agricultural commodity till really just quite recently, only really over the last 20 years. This is a picture of the Sapphire Energy site down in Columbus, New Mexico. That happens to be a 100-acre facility of algae ponds. They were using it to do biofuels. When biofuels kind of went bust because the price of oil dropped, it got converted and now it's used to grow an algae that they make omega-3 fatty acids from, Nanochloropsis. So we can take this to world scale. It's unlikely that it'll be lined, expensive ponds like this. When we really go to big scale with it, it'll probably look something like this. This is a picture of a rice paddy, super cheap to make, maybe less than $200 an acre, kind of expensive to make, several $1,000s an acre just to develop the system. So we'll do it in something like this, but we can take it to world scale. That's the important thing. As I said, originally we started out to make biofuels in this guy. That's, Sapphire Energy, one of the companies I started, raised a boatload of money. The premise behind that was pretty simple. Petroleum is fossil algae oil. It's not melted dinosaurs. It's not a geological deposit, right? It is ancient algae that grew on this planet back when there was very high levels of CO2. They pulled that CO2 out. They fixed it into oils. The algae sank to the bottom of the oceans and bays they were in, covered with silt and sand. Over time, that became petroleum and natural gas. So the idea behind biofuels was simple. Well, since petroleum is just fossil algae oil, let's just grow algae in real time and convert it. And we did that. It was actually quite easy to do. These happen to be pictures of our greenhouse, but you grow the algae up. It can hit densities, pretty good, a gram per liter, something like that. Some as high as 5 or 6 grams per liter. So, you You can, and then you take the oil on the top half, that goes into a refinery, can be converted into jet fuel, into diesel, you name it. Proteins on the bottom can go off to feed animals. So that was the idea behind it. Why didn't this ever stick? This never stuck because we could not get down to compete with petroleum drilled and extracted out of the ground. When we started this whole enterprise back in about 2007 and 2008, we were up around 20, 25 bucks a gallon with the best estimates then. We did an analysis at Sapphire early on, said we thought we were at 21. But we said, hey, look, there's a variety of things. Bioprospecting means we go out and get better strains, start to domesticate them. Engineering meant more of the engineering system, breeding and selection to get better strains, and then eventually co-products. We sort of projected that sometime around 2017 or 2018, we originally had this line crossing over and passing, becoming cheaper than petroleum in about 2018. That didn't happen because in 2015, the price of oil went from 100 bucks a barrel to 30 bucks a barrel in about a 6-month period. And when that happened, all investments into algae for biofuels just completely disappeared, dried up and blew away, right? But we had developed a lot of technology. So many of us turned around and said, hey, look, we know now that we can grow algae at large scale. Let's go and do it, but let's pick something that has a higher value than, fuel that you're going to burn, which is always the lowest value, right? And in fact, it's only about 30 cents, 25 cents a kilogram, right? So anything's more valuable than that. You can get some things that are super high value, like maybe nutraceuticals or pharmaceuticals. We sort of opted to pick guys that were in the middle. We said, okay, let's go after two things. Let's go after food, and then let's go after polymers, right? Okay, so food. So we started down food, and the idea behind that is really simple. Algae can produce high protein content, high lipid content, makes a lot of nutritious things. We can grow it. Let's think about just growing this and turning it into a food, either for animals or humans. So this is just one algae. Algae are thousands of different species. There's a bunch of them we can look at. They are all subtly different, but this is just one called Chlamydomonas reinhardti, very common lab strain. Now it's into production several places. That algae produces protein in about 47% of its biomass. Just to tell you where that ranks, soybean are about 38%. So the gold standard for protein, soybean 38. This algae is 45. You get some that are up as high as 60 or 65, right? They're also very rich in omega-3 oils. We all know those are good. And they make beta carotene, iron. So lots of good, healthy, nutritious things for you. And a very nice balance of amino acids, okay? So you look at this thing and, well, okay, algae should be pretty good as a food. But you don't just get to take, an algae out of the wild and just go start feeding it to people. Some people do. You're not supposed to do it that way. What you're supposed to do is go to the FDA and prove that it's safe. You don't have to prove that it's nutritious. You just have to prove, hey, if you eat this stuff, I won't make people sick. So how do you get that? That's called generally recognized as safe, or GRAS. So we went out and got GRAS status. We grew our algae up. We fed it to a bunch of mice. We fed it to a bunch of rats. Eventually, we fed it to a bunch of pigs. And we showed that, hey, they could not only didn't get sick, but many of them had some noticeable benefits, especially the pigs. The one thing we noticed when we were feeding this to little piglets was they seemed to have significantly less diarrhea than the ones on the standard pig feed, right? So we were eventually given GRAS status on this from the FDA. And then we said, well, let's go out and actually do a test. So what test were we going to do? We decided that we were going to go out and get a bunch of human volunteers, and we were going to feed them our algae, and we were going to find out, one, do they like the taste? Two, will they eat it every day for 30 days in a row? Like, I don't know, maybe they'll decide, I hate this, or it's not good, or whatever. And then because of the pig study, we also said, hey, let's pick both healthy individuals and people with something called irritable bowel syndrome, right? Upset stomach, diarrhea, very common. 20% of people have it. Stress, diet, a lot of different things cause it. It's unclear, genetics, right? But with the pigs, we thought, hey, it improved pigs who had something like IBS. Let's see if it'll improve that in humans. So we went out and got about 100 different volunteers, of which about 11 of those had IBS. And what we did was we just asked them to eat algae every day, 1 gram or 3 gram. 1 gram was the 1 gram was our low diet, 3 grams was our high diet. And here's the two different groups. So the top one right here are people who reported, hey, I don't have any gut health issues at all. And all we simply asked was one really simple question. If you eat the algae every day, do you have less bowel discomfort, less upset stomach, and less diarrhea? Do you have either one of those? And what you kind of see in the healthy individuals is they went from rarely to never. So there was some benefit when you're climbing. If on these kind of spider graphs, if you're going to the right and you're going up, things are getting better. So you can kind of see they got a little better, but with healthy individuals, we saw a change, but it wasn't a big change. But oh man, with the people who had IBS, we saw a significant change. Here are often I had diarrhea or discomfort to rarely. And you can see those populations really jump. This is the composite of it. So in other words, our algae was not only nutritious, we were not only giving people benefit of getting good amino acids and good carbohydrates out of it, it actually seemed to have some very good health benefits too, right? In addition to that, we actually went through every one of these individuals and looked at their gut microbiome because we had some idea, I mean, it was well known actually, that people with IBS tended to have much less complex gut microbiomes, and healthy people tended to have more complex ones. So we wanted to see if algae impacted that. Sure enough, it impacted it dramatically. I can't show you microbiomes of other individuals because that's considered private medical information. So here's mine, right? And it's very hard to tell, except but I'll just sum it to say is my microbiome was very complex when I started. I did not suffer from IBS. I became my microbiome shifted from looking more like a meat eater to looking more like a plant eater, like a vegetarian over time. And the complexity of mine went up, not significantly. I had about, I want to say 40 different organisms that could be identified, and eventually that got to about 65. But people with IBS, some of those had as few as 6 or 8. They got up into the 30s and 40s. So great benefit to it. Now, but how does that really impact at a big level? Why would we think of algae as a future food? I hope you guys all know what the Impossible Burger are. There's lots of these things now. Many, many different ones are out there. Some people call them plant-based meats or meat substitutes or whatever. But the basic idea behind whether it's Impossible or any of the other ones out there is that it's a much lower environmental footprint on the planet. Impossible Burgers happen to be made from wheat protein, coconut oil, potatoes, and cloned leg hemoglobin, right? But what they say is we get a 96% less land use, 87% less fresh water, and 89% fewer greenhouse gases. That is compared to if you're eating an Impossible Burger compared to beef, compared to a normal hamburger. But remember, algae are 10 times more efficient than soybean or wheat at producing proteins, which means if we could make an Impossible Burger from algae, it would have an enormous benefit. One of the companies I started called Triton Health and Nutrition, they actually make a little dumpling. So it's a pork substitute. It's all 100% plant-based. They actually use algae only at a small percent. It's about 5% of the total content of the protein because it gives it that kind of savory pork flavor and that slight little pink color that's pork, right? And these things used to be available at Costco down in Texas. I don't know if they still are or not. I haven't got any lately, okay? But this could be a game changer for the planet if we could do this one thing, all right? And then I want to, so I actually think that if you wanted to do something for the planet to dramatically improve climate change or reduce climate change, I guess I would say, it would be convert all of beef into synthetic, plant engineered beef and use algae as the source of that. That alone would unbelievably reduce the carbon footprint of human beings. Okay. And there are lots of companies that do it, whether it's Impossible, Beyond, you name it, everybody's out there. If you had to make a choice, I tell the students in my class, if you have to make a single choice, stop eating beef and start eating fake beef, plant-based meat substitutes, and you'll be doing as much for the planet as anybody else out there. Okay. But I wanted to do something ourselves too, right? And so, as I said, when we were running, Sapphire, the basic idea behind it was, right, petroleum comes from algae. So rather than pull the fossil stuff out of the ground, let's just grow it real. Well, here's one step beyond that, and that is plastics come from petroleum. Petroleum comes from algae. So let's make plastics from algae. Super simple idea. I have algae, it grabs CO2 out of the atmosphere, it converts it to oils. I convert those oils into polymers and I make products with those polymers. And then, since we're going to reinvent these plastics, let's do them in such a way that they don't accumulate on the lands or the ocean. So let's make them so they biodegrade. All right. That was the first idea we had. Hey, let's just make biodegradable plastics. And if you look around, there's actually a couple of plastics that are quite abundant out there that are used that actually naturally will biodegrade. Those are all the polyesters. So that could be polyester polyurethanes, polylactic acid, that's a polyester, polyhydroxyl butyrate, or sometimes these things are called polyhydroxyl alkanates. There's a big class of those. All of those things will naturally biodegrade. We have done stuff to them as chemists over the last 50 years to keep them from biodegrading because we thought that's what we wanted. We wanted plastics that last forever, but we at least knew that there was the potential there to do that. So we simply went back and said, okay, let's pick one of these, and which is the one we should pick? Let's pick polyurethanes. And we did that because number one, they're very abundant, but two, they also made some kind of cool products that we could relate to. One is they make rigid foam, so we could make surfboards. We thought that was important. Two, they make soft foam, so you could make shoes or flip-flops, etc. And then you can also use them for coating and elastomers, like you can coat coats with them. And we'll show you in just a minute that we've actually done all of those things. So what is a polyurethane? Polyurethane is super simple. You have one portion of it, which is called a polyol. And a polyol is that little R can be as many carbons in a row as you want. Could be 10, could be 200. And then you have an alcohol on either side of it. So you have to have two, hence polyol. You can have more. You can have 3, 4, 5, whatever, but you have to have a minimum of two. Then you combine that alcohol with an isocyanate, and an alcohol and an isocyanate link together to make a urethane bond. And so if you have two isocyanates on a molecule and two polyols, as they link together, you get polyurethanes. So super simple, all right? So what did we do? We took our algae oil and we made it into polyols, and we combined those polyols with petroleum-based isocyanates, and we made rigid foams. And with that rigid foam, we made a surfboard. This is Mike Burkhart. He's chairman of the Department of Chemistry at UC San Diego, longtime collaborator. So Mike and I made that surfboard. The guy there with the mask on is Marty Gilchrist. Marty owns the company called Arctic Foam that actually makes most of the blanks that are turned into surfboard. So we made that thing. We made a surfboard. It completely went viral. That surfboard traveled all over the world. It was on the news, NBC News. National NBC News reporter came down and surfed it. It made a big splash. Because of that, we were then contacted by one of the big shoe brands. This was back in 2019 and 2018, and they said, "Hey, if you guys can take algae and make rigid foams, we bet you can take it and make soft foams." Soft foams are a much, much bigger market than rigid foams. There's only about 500,000 surfboards sold per year. Believe it or not, there are 25 billion with a B pairs of shoes made every year. So just in terms of mass, shoes was the market you wanted to go into. Okay. But it took us a little while. I mean, think about that. Here you have this little piece of foam right here. And this guy who might weigh 200 pounds, so 100 kilograms, he is going to land on that shoe sole with all of his weight maybe 50, 70,000 times, right? And every time that weight is going to smash that shoe down, how much it recovers or fails to recover, that's called the compression set. It means when you compress it, how much of it stays. That actually turned out to be a very difficult metric for us to hit. We could hit density, we could hit elongation. Those things were pretty easy. Compression set took us a while. What is that process? You're changing both the background materials, the polyol that you make and the isocyanate you use. You're also mixing in lots of other things, surfactants and catalysts and pigments. And then the way you process them, the machine that you put it into also impacts that. So finally, in January of 2020, we finally had foams that met specification. We were so excited. We're like, this is so great. We finally have one. We were talking to the big shoe brand. They're like, let's go into production. And then in March of that year, the world pretty much shut down. And we were told by many of the shoe brands, we're not going to open up again for at least a year. And we decided, well, that's kind of unacceptable. Man, we spent all this time. So what are we going to do? You know what? We're going to go and make our own shoe. So Mike and I actually hired a guy, Tom Cook. He came out of Vans, and Tom designed the shoes and brought in all of the shoe dogs, as they're called. And we went down to Mexico and visited those guys a bit. We ended up landing in Indonesia at a factory over there, made our polyols, shipped them over there, got the isocyanate, shipped them there, and we actually built our own shoe, right? Again, it took us about 2 years to do this. Took us about 6 months just to train the guys in the factories how to use this, but eventually we did, got them to work, brought them back, and we started selling these things, right? And so in April of 2022, 2 years ago, now a little more than 2 years ago, we actually put these things on the market. Now, that was not our mission was not to become a shoe brand. Our mission was to sell our materials, our sustainable materials, to every shoe company in the world, so we could really have a global impact, right? But interestingly enough, once we had the proof of concept, all of the other shoe companies bought them. Like our first 8 shoes went to Portland, Oregon, which is where Nike and Adidas are, right? But a bunch of other shoe companies bought them as well. They looked at them. And so then we actually started to sell these things. But we actually had to prove, okay, you say these things are biodegradable, and theoretically they should have been biodegradable. We made sure that we did the chemistry so that we didn't make them not biodegradable. And so we had to prove that, right? And so what is this? Here's one of our shoes, right, called the Blue View Pacific. And here it is at 1 month, 3 months, and 6 months in a home compost pile. So this is not industrial composting. We're not treating them with chemicals or anything else. Just put them in your home compost pile. At 6 months, you could barely recognize in a shoe. By 9 months, you couldn't see it at all, right? Well, how do we know that that's not just, being abraded and turning into microplastics? Well, if it was fully biodegradable, you can measure the CO2 that comes off that. Here's paper. It degrades very quickly. Here's our shoe. It degraded, eventually got to 100% conversion of our foam into CO2. It's called mineralization, right? And then, we did some scanning EMs to show that there were actually organisms that were getting on these things and eating them. Okay, so that's in compost. Well, what happens in the ocean? We actually strapped a pair of our shoes onto the pier here at Scripps Oceanography in the ocean, because ocean water's colder than it is in a compost pile. Compost piles can get up to about 37, 40 degrees centigrade. The ocean, at least the one out here in front of us, is only about 15 degrees centigrade on average, right? So it degrades slower, but the process was exactly the same. And importantly, the organisms that degrade it were similar, not the same because the ocean, but same genus, different species, okay? But here's the kind of alarming thing that has shown up over the last year, and that's that we started to see all these papers about nanoplastics and microplastics are everywhere. And this was one that really was kind of alarming. They're in people's arteries. And if they were in your arteries, there was a correlation between your risk of having heart disease or stroke. And in fact, the people who had high levels of plastics were 400% more likely to die from a heart attack or a stroke. And then, as I said at the beginning of this, now we've seen ones where 0.5% of our brains potentially are microplastics, okay? Well, if a plastic biodegrades, it shouldn't form persistent microplastics, but we had to actually prove that, right? And unlike most other shoe companies or chemical companies, we actually go out and prove our stuff by publishing it in peer-reviewed journals. So here's what we did. We did 2 things. We took a phone case that we had made with one of our polyurethanes and a shoe, and we ground them up with a belt sander and turned them into microplastics. Then we mixed those microplastics into compost, and then over time, we took samples out, extracted the microplastics out, and visualized them. And then with the second group, we actually looked at the conversion of the microplastics into CO2. So going all the way from plastic to bacterial or fungal biomass, plus CO2. That process is called mineralization. And then we also looked at, well, what are the organisms that are eating this? We're kind of curious to know what those were. Okay. I won't go through all the data except to say that sure enough, both our thermoplastic polyurethanes and our foams, the microplastics generated from those degraded very quickly, some of them in as little as 100 days, almost as fast as cellulose. Here's a visualization of one of our foam cases, so a thermoplastic polyurethane that we use to make foam cases or to coat fabrics like in a raincoat. Here's day 0, lots of little fluorescent microplastics. By day 200, very few. Here's our sort of a standard petroleum-based, very common plastic called ethyl vinyl acetate. After 200 days, no change at all in that, right? As predicted, okay? As I said, we also looked at mineralization of these things. Yep, sure enough, they're not just microplastics that are getting smaller and smaller and becoming nanoplastics, maybe that you can't see under a microscope. They were actually going all the way back to mulch and CO2. Predictable, right? But we had to do this and we published this. And interestingly enough, when we published that paper, which we did in March of this year, by April, we were getting calls from lots of different companies, right? We also identified the organism. Turned out that a rhodococcus and a bacillus were kind of the main guys. Kind of interesting. These organisms had been seen chewing up on a few other kind of interesting plastics. But in ours, we actually found a rhodococcus species that would live on our polyurethanes as a sole carbon source. So not only were they getting the carbon out of it, they were also getting the nitrogen out of it, right? And so we now have a plastic that can go all the way from a highly functional product back into CO2 and microorganisms in as little as 100 days. And some of these, we want them to last a little longer than that. So we've learned how to kind of stretch that out and keep it going a little farther, okay? We obviously visualize this just to see how these guys are going. And it's no different on our plastic than it is on everything else. The organisms colonize the surface of the plastics. Here's a fungus. You can see some fungal strands up here. These little dots right here. This happens to be the rhodococcus strain. Here's the fungus. I think you can see one of them kind of winding around over here. What do? They secrete enzymes. Those enzymes get in and break the polyester bonds and the polyol, or the urethane bonds between the isocyanate and the polyol, and then they just eat the small molecules that pop out of that, all right? So no different than if they were eating cellulose or if they were eating, a hamburger, right? Its biodegradation is easy to measure. We've been told by lots of people, lots of different groups, oh, I don't really believe this. Plastics can't biodegrade. Or a very common one, which we hear from lots of companies, is biodegradation is so complex, no one can really know whether it degrades or not. The people who are telling you that have non-biodegradable plastics and they want to protect their market. It is super easy to tell if something is biodegrading or not, right? You can see the organisms eating it. You can see it physically disappearing. You can measure the CO2 that's coming off it. These things are clearly biodegrading as we publish, okay? This just happens to be coated fabric. We can make raincoats out of our stuff. If you make a raincoat and use our polyurethane to coat it, it turns out that the cotton underneath here in the fabric wicks moisture in. They degrade at a really quick rate. Like, we could not distinguish this raincoat from compost in 50 days. So these things are actually degrading about as fast as cellulose paper does. Phone cases go a little slower. They're more rigid. They tend to exclude water. They smooth surface, hard for things to colonize them. But we have phone cases that have completely disappeared within about a year and a half. All right. Now, the one last thing that we had to show was, okay, you've made a polyurethane, you made it from algae oil or plants oil. You predict that it's not going to cause anything bad when it biodegrades. Prove that to us. And the way you do that is the compost that we degraded our shoes in. We use those to grow corn. And this is just a video showing that whether it's corn grown on compost with cellulose in it or compost with our shoe in it, they grow exactly the same. So no residual toxins left there, right? Okay, so we've made food from algae. That looks like it could be very nutritious. Those markets are starting to build. People are starting to take it up. We still got a ways to go on that one. But I think we're at least on a path now where we could see if people will just change their attitude, right? We don't have to make a better product. The invention is here. The invention is ready to go. We just need people to start to eat those things and to stop eating what they did yesterday. Probably going to take 20 years, but it seems like that's coming, right? Biodegradable plastics, I think, are essential for the planet, right? We're asked all the time. In fact, I've been asked by senators and congressmen, do we need to pass legislation to ban plastics that do not biodegrade? I think that would be a good idea. I think that is something we should consider. But what I'll tell you is, it is very unlikely that legislation is going to get plastics off this planet, right? Because there's just too much money, too many financial people with financial interest in this, too many big lobbies that will fight it. We will never be able to pass it and get rid of them all. What is going to get rid of it? Litigation. I have now been contacted several times over the last few months by lawyers, by big law firms asking if I want to be an expert witness in lawsuits that they are having against the big petrochemical companies. Why? Because if you die of a heart attack, right? If you're 50, 60 years old and you die of a heart attack, first thing you do now is do an autopsy and find out were there microplastics in your arteries. If they were, we already have established there's a correlation between those microplastics and your cause of death. You now have a cause of death, which is due to microplastics. What am I going to do? I'm going to go sue the company that made those. And sadly, what I can tell you is since we published our paper in March, we have been contacted by the big brands, not the chemical companies. We have been contacted by the consumer brands, by the you name it shoe company or you name it outdoor gear company, asking us, hey, do you guys want to do a project with us? Why? Because they're trying to limit their liability. They want to be able to tell people, well, we didn't have a choice. We had to use, PFAS in our waterproof, and we had to use polyvinyl chloride in our waterproof coating, right? Well, now we found out those are, forming microplastics. Let's do something different. So it will be the litigation that will get rid of it. Same way that's what got rid of cigarettes essentially in this country. Then over time, I hope people will kind of understand better their responsibility for it. Okay? At any rate, I say we are out of time, or at least I think we're out of time. So I'm going to end it right there. And I will see if we can organize any questions. But I'll just say one last thing. For the last, I don't know, 2 decades, really, I've had this idea that, it's fun to do research science. And I've published, I don't know, more than 200 papers now. I don't know, Science Citation Index above 72. So, all that stuff was fun. It was a good career. But if you really want to change the planet, sadly, it's not publications that do that, it's products. Make a product that people can buy that improves the quality of life for you and the rest of the organisms on this planet. So we started this company, Mike Burkhardt and I, called Algenesis Materials, in which we are commercializing these and trying to sell our products. So if you have any influence on the big brands out there, your favorite shoe brand, your favorite clothing brand, you call them and tell them they should call us up and find out how they can use our material. Okay? And I will stop sharing right then. And
thank you, Stephen. That's totally fascinating. We do have a lot of questions that have come in on the back, so I'm gonna. I think we have enough time to address most of them.
Okay.
So the first one is that the results of the IBS study in the American gut data set, or do you keep them private?
No, we do not keep them private. We published a paper on that back in, I want to say, 2018. Just Google my name and you'll find it. I'm pretty certain it was published in 2018. If not, I can send it up to Mauricio and share it with you guys. So we published that paper. A couple studies have been done since then by the company. Those they have kept private because they are trying to identify, can we specifically target people with IBS? So those data have not been published, but the basic study was.
Right. Mahmoud is asking, nice talk, Dr. Mayfield, regarding the higher oil prices in the last 3-4 years, $60 to $80. Could you envision biofuels, algae-based biofuels, to return to the market more competitively in the near future?
Yeah, funny. The magic number that people always threw around was $80. If it got back above 70 was like, oh, can we compete? $80, we knew we could compete. Every time oil goes above $80, I get a call from somebody saying, hey, let's go back. So here's the reason we're not gonna do that is because in capitalism, you don't sell your product to the lowest bidder, you sell it to the highest bidder. Almost everything can outbid fuel. So until we have saturated the food markets, until we've saturated the polymer markets, until we've saturated even the fertilizer markets are more valuable than fuel. So until we've saturated with all those markets, we won't get to fuel. Will we eventually get there? Yes, but that's going to require an economy of scale and production that is way above what we're doing right now. So that's still, I think, decades away.
Excellent. And then uh, the next question is, what are common ways that people can get nanoplastics? And I'm assuming the question means nano and or micro
Yeah.
plastics in their arteries.
So it comes through the water. It comes through your drinking water. If you were to go and just take your tap water right now, especially here in San Diego where we recycle ours, even though they've gone through reverse osmosis, there's still lots of microplastics in there. It's unclear if drinking out of a plastic water bottle is enough to give you that, but it probably does. But they're so ubiquitous. They're in the air we breathe, they're in the food we eat, they're everywhere. Here, I'll give you one example. We were approached by a group that grows carrots. And apparently, at the end of every season, they cover their fields with plastic so they can fumigate them. And the plastic is so thin that they don't have any way to recover it. It just becomes microplastics, and they knew it. And after doing this for 10 years, people have now analyzed their soil and they're not going to be allowed to grow carrots on it anymore. It's too high in nanoplastics. So I would say the most important thing you guys can do is get a water filter on your home water system, right? It doesn't have to be a reverse osmosis. Just those charcoal and the other activated ones are pretty good at pulling it out. But get one of those. It'll help you on health and taste better too.
And a question still on this health impacts. Are there any potential health risks or to regular consumption of marine algae?
No, what I'll hear all the time is people will say, well, don't algae have toxins? How about toxic algae bloom? So there are thousands of species of algae. A very small set of the cyanobacteria produce toxins that are harmful to animal or people. And we don't eat those. We don't grow those commercially and feed them. You know, in the same way that I've yet to go to a grocery store and see poison ivy or poison oak sold in the salad bar. You have to know what they are. And it's true, they kind of look the same. So you have to know. But no, there's the algae that we grow are very safe and they do not produce toxins.
Excellent. Um, I have a question from a former student of yours.
Yeah.
He says he took your biofuel course.
Okay.
And
Yeah.
the question is about methodology that you used to quantify microplastics in
Yeah.
water.
Yeah.
Were you using FTIR,
We,
which the student is actually developing and doing research on?
okay, good. FTIR is a great way to do it. That is not what we did. We simply found a fluorescent dye. We got this out of the literature. We didn't develop this that binds to plastics at very high levels. And then we visualized them by putting them into a microscope and counting the little spots. We also used a mass spec just to look at the average size of the particles coming out so we could show that ours were decreasing at a rapid rate where the ones that don't biodegrade sort of stayed at a constant size.
Excellent. Uh, Dr. Karim Hosseini has said, why are the food applications of algae really not taken off?
Yeah, for the,
How are they? How do they taste? What can be done to make them tasty?
okay, I'll tell you one quick little funny story about that. A good friend of mine is down at Arizona State University and is famous for developing the Cheetos taste, right? So he's not a nutritional scientist, he's not a food scientist. He studies sort of marketing and people's acceptance, right? I called him up because I said, hey, Mark, we're about to put this algae out. All of us eat it and taste it, but it doesn't taste like anything we're familiar with. Should we modify the taste? Because you can. It's a microorganism. You can select for ones that taste different. And what he told us was no how, no way. Do not change it. And the reason I'm telling you that is once people find out how healthy it is for them, they will learn to like the taste of it. Okay, forward a few months, we're doing our study, everyone's eating it. I'm reading the daily reports that they come in, right? Because the 100 people in our study, we ask them, hey, every day, would you just log on for a minute or two and just tell us how you're feeling that day, what you're doing? And what I immediately saw after about a week was, oh my God, the people with IBS, this is profound. This is not a subtle change. There are people now after a week telling me, I don't have any diarrhea. It's been 5 years that I've had this. I don't have any stomach aches. I'm not bloated and full of gas. This is a godsend. So I'm reading these things every night and realizing, holy smoke, this algae is actually really good for you. As I'm reading those, I'm liking the taste more and more and more. And by the time we were at the end of the 30-day study, it was my favorite taste. That's what humans do. They learn to associate a specific taste with a good outcome. They learn to like it. Okay. But the reason it hasn't taken off, the bigger question is, why hasn't it taken off? Because we want to do today what we did yesterday, changing people's attitudes. And I'll give you one great example of this: photovoltaic cells, right? In California now, we're at about 55%, renewable energy from photovoltaics. We could have been there 20 years ago. Why weren't we? A, they were a little bit too expensive, but not much. 20 years ago, they were already affordable. We just didn't do it. It took us 20 years. Now, if you buy a new house and don't put photovoltaics on it, you're a knucklehead. You're paying way more for your electricity than you have to. So it takes a generation. And that's true whether you're talking about iPhones and people accepting the new, those new smartphones, or whether you're talking about something like algae. It's going to take 20 years. There's no way around it because it's humans.
Okay, so we are definitely over time, but we'll keep getting some great questions. So I'm gonna bear with you and
Okay.
our audience and ask the rest of them.
Okay.
Um, the Have you experimented with algae in cellular agriculture? How do you address the inherent limitation of plant-based scaffolds, such as challenges with cell attachment and
Yeah.
proliferation?
Yeah.
Additionally, how algae impact the final sensory property of the product?
Yeah. So let me answer the last one first because that's easy, right? So because there are thousands of different species of algae, you can impact flavor, you can impact smell, you can impact color, you can impact all of those things. And so there's no answer for that other than to say you have an enormous palate. And so you have an ability to change a lot of different things. With Triton, the little dumpling that they were making, that was just coincidental that the algae they were using gave a slight pink hue to the fake pork protein. But that turned out to be really important. People looked at it, they said, oh, that kind of looks like cooked pork. So lots of ability there, but no simple answer on that, right? On the other one, the toughest thing to do, these companies that are trying to do single cell agriculture, the toughest thing for those things is those generally come from multicellular organisms. And then we've selected those so they'll grow as single cells, but they weren't really made. They didn't evolve to do that. And quite often their immune system comes from a different cell. It doesn't come from the single cell you're growing. Algae were single cells. They have an innate immune system. That gives them an ability to go to really high scale, and you don't have to be a super clean environment. That's why bacteria work. That's why yeast work. That's why algae work at big scale. Much tougher to do that when you're trying to propagate a fish cell, the companies that are trying to do these single-celled agriculture for, salmon or for pork or beef. That is going to be an incredibly tough lift because of the immune system, because of the lack of the immune system in those single cells. We have it. Algae have it.
Interesting. And there is a related question, which I think you probably have just answered, but how are issues like contamination and uncontrolled algae growth managed in large-scale biomanufacturing?
Yeah, so there's two answers to that one. One is if you're outside, and one is if you're in fermentation. If you're in fermentation, there are lots of companies that grow algae strictly by fermentation. Easy to handle, right? You can have a sterile environment, you can inoculate them, they grow very quickly. You're good on that. When you're outdoors, what we have done is we have switched to something called an extremophile. If you look at the algae that have been grown, and some of them have been grown historically for hundreds of years, they're extremophiles. That means they grow at high pH and in high salt. And when you do that, they tend not to be contaminated either by other algae or by predators that eat them. So we actually went out and selected, we went out and found bioprospect all over California and found an algae that is a green algae, super high in omega-3s, very nice, grows at pH 10.5. And so when you grow that guy outside at pH 10.5, there are just not many competitors that come along. So we can do management that way.
Great. And we're going to wrap with uh, a couple of business points.
Yeah.
Sandy would like to know where she can buy the biodegradable shoes.
Okay, the biodegradable shoes are on blueviewfootwear.com. So if you just single word Blue View, just type in Blue View footwear and you will find us on our webpage. Okay.
And I'll tell our audience that Stephen was kind enough to send me a pair, and I use them faithfully for my water-based activities, and they're great.
Yeah.
And then last question, it's a follow-on from a prior question. Uh, could improvements in genetic engineering techniques to enhance lipid productivity of algae or biochemical conversion methods of lipids to biofuel make algae biofuel the ultimate substitute for fossil fuels?
Yes, they could. But as I said, again, until we have saturated, for example, the omega-3 markets and the polymer markets, it's unlikely that we'll go to fuel. With car electrification now, it's kind of most transportation, cars, trucks, things that are on the ground. Electric engines are way more efficient than internal combustion engines. We're going to go that route. It's clear. I own an electric car. I'm on my third one. I've got the little Chevy Bolt. Things are fantastic. Once you get an electric car, you're never going back. Airplanes, almost impossible to electrify. Boats, almost impossible to electrify. Those are the two places we're going to need biofuel. So yes, we can get to those, but again, not till we've saturated the food and the polymer and the nutraceutical markets.
Excellent. Well, thank you so much, Dr. Mayfield, and thank you to our audience. And if there are further questions, you can forward them to the Terasaki Institute, and we'll make sure that Dr. Mayfield sees them.
Thank you. Thanks,
Uh,
everybody.
thanks, everyone.
It was a pleasure. Thanks, Mauricio. We'll be in touch soon, I'm sure.
Absolutely. Take care.
Okay, cheers.